This is another example about Solow Growth Model. The question is, consider an economy with the production function of our total output equal to technology multiplied by capital to the power 5 over 9, labor to the power 4 over 9. This is a Cobb-Douglas function, that's why the summation of the power will always equal to 1. The first part of the question is part A. Demonstrate that the per capita production function for this economy is our little y, which is our output per capita, is equivalent to technology multiplied by capital per capita to the power 5 over 9. So I would like to get this one from our original Cobb-Douglas production function. So I will write my production function here as y equal a k to the power 5 over 9, n to the power 4 over 9. I will move it from a fraction into a decimal. So 5 over 9 here is equal to 0.56. 4 over 9 is equal to 0.44. Then I need to divide by labor. So I will get y divided by n, and on the other side, I will divide it by n as well. So here I have n in the numerator and n in the denominator. So I need to take n from a numerator to a denominator by swapping the sign. So I can write it as y divided by n equal a multiplied by k to the power 0.56 divided by n to the power 1 multiplied by n minus 0.44. Since I have the same variable and different power, what we're going to do is I will get the summation of the power. So n to the power 1 minus 0.44, it will give us n to the power 0.56. So this means that y over n equal a k to the power 0.56 divided by n to the power 0.56. What I will do now is, since I have the same power here, so I will get k and n in one bracket, all of this to the power 0.56. So I will get here y over n multiplied by a equals a multiplied by k over n to the power 0.56. So here y over n would refer to per capita output, which is little y. K over n, it refers to per capita capital, which is our little k. Therefore, we can write our formula as our little y is equal to a little k to the power 0.56. So now we prove that this formula is exactly the same as this formula. The second part of the question. For population growth or labor growth of 25%, depreciation rate of 37.5, savings rate of 4 over 9, and technology 22.5. What are the steady state values for output per capita, investment per capita, consumption per capita, and capital per capita? So from the previous videos, we get our capital at the steady state, which is savings rate multiplied by technology divided by depreciation rate plus population growth, all of this to the power 1 over 1 minus theta. So let's substitute. What's our saving rate? 4 over 9. What's our A? 22.5 divided by what's our depreciation rate? 37.5 plus what's our population growth? 0.25. All this to the power 1 over 1 minus theta. Where is our theta? 5 over 9. Use your calculator, you will get our capital per capita at the steady state, which is equal to 512. Let's continue. So we just calculated k as 512. So we solve it for k. What we need to do now is to solve for our per capita output. So in order to get our per capita output, I need to write our per capita output function. So I know that our little yt equal a little kt to the power theta. And I put here t, it refers to the time. So let's substitute. What's our a? 22.5 multiplied by capital, the one we just calculated, 512 to the power theta, which is 5 over 9. This will give you our per capita output of 720. So we calculated y. Then we need to calculate our per capita investment. So we know that our per capita investment is equal to saving rate multiplied by per capita output. So let's substitute. What's our saving rate? 4 over 9. What's our output? The one we just calculated, 720. So if I multiply both of them, I will end up with our per capita investment of 320. And this will be our little I. Then we have our little c, which is per capita consumption. So the formula for per capita consumption is anytime you have an income, you will divide it into consumption and savings. In the long run, savings is equal to investment. So our Little c is equal to little y, which is output per capita minus investment per capita. Let's substitute our output per capita, we just calculated 720, minus investment per capita 320. It will give us our per capita consumption of 400. So we solve it for the 4 variables. Then, draw the per capita production function supporting curves to capture the economy at its steady state. So I'll start with our y-axis, which is output per capita. I will draw our x-axis, which is capital per capita. And then I will draw our production function, which has a concave shape. Why? Because of the law of diminishing marginal return, which means anytime we increase an additional unit of capital, its productivity would be lower. MBK will be lower. Then I will draw our investment function. And investment function will be concave as well. And anytime we make an investment, we know that we cannot use a machine forever. That's why we have a depreciation. Plus, anytime we hire a new labor, we need to give them capital. And that's why we call it the maintenance cost. Therefore, our maintenance cost is a straight line. So here we have maintenance cost. Then I would like to get the steady state. We know that the steady state is the point of intersection between our investment and the maintenance cost. Let's look here. The point of intersection between our orange curve and the green curve, it will be this point. Then from this point, I will go vertically to get our capital per capita at the steady state till it touches our production function, and then I will go horizontally in order to get our output per capita. And here, as we just calculated, we know that our capital per capita at the steady state is 512, and our output per capita at the steady state is 720. So, from our steady state per capita capital, I will look at the investment function, and then I will go horizontally, and this will give us our investment per capita. And previously, we calculated investment per capita as 320. Therefore, I know that this area refers to our investment per capita of 320. Consequently, the difference between output per capita and investment per capita will be our consumption per capita, which is little c, which is 400. Then, the next part of the question is demonstrate. Our next part of the question is demonstrate mathematically that the golden rule saving rate for this economy is equal to 5/9. So if you check here in our production function, this 5/9 refers to what? It's the power of k, which means this is equivalent to our theta. So what do we mean by the golden rule? Our golden rule refers to we need to maximize our consumption. And that's why we write it our CG. G refers to the golden rule, which means the maximum consumption. So what do we mean by maximum consumption? Anytime we have lower capital, what will happen? We have lower consumption because we don't invest much. Consequently, the output will be very low. But what will happen if we have a high level of capital? What will happen to our consumption? We discover that because of high level of capital, what will happen to our maintenance cost? It will be high. Consequently, what will happen to our consumption? Consumption will decrease as well. That's why if I would like to draw the relationship between our capital per capita and consumption per capita, so I will draw it here, I will discover that our consumption function will be a concave shape, which means at a low level of capital, we have low consumption. At a high level of capital, we have low consumption as well. Consequently, in order to get our maximum C, I need to look here, where is the highest point? So this is our highest point. So from this point, I will go vertically in order to get the golden rule capital per capita, and consequently, it will give us our golden rule consumption per capita, which means at this point, we have our maximum consumption. And I will put here little g, which means this is our maximum consumption. So let's do it mathematically. In order to get maximum C, I know that our C equal to little y minus little I, which means output per capita minus investment per capita. So at the steady state, we know that investment is equal to maintenance cost. Let's write the function of investment. So it's saving rate multiplied by our output function, which is a function of k, equals maintenance cost is depreciation rate plus population growth multiplied by capital. And I put here a star, which refers to the steady state. So in order to get maximum C, I will substitute in our original formula here. For output, I will put a function of k. For investment, I will put it as maintenance cost, G plus N multiplied by K. So in order to get maximum C, we need to get the first derivative and then equate it to 0. So in order to get the first derivative here, for function of K, what we will do is I will write f prime K. F prime K, it means that this is the first derivative of our production function. And then here I will get the power of K, which is to the power 1 here. So it will be 1. And then I will subtract 1 from the power. So here it will be 0. Anything to the power 0 is 1. So I'll end up with G plus N. Then I will equate the first derivative equal to 0. So I know that the first derivative of our production function, which is f prime K, G, because I refer here to the golden rule, equal D plus N. I know that the first derivative of a production function is called marginal product of capital. And that's why I could say that our D plus N is equal to marginal product of capital. Let's continue. So I will start again from the steady state. So I know that our investment is equal to maintenance cost. So let's solve it. Here we have our investment is saving rate multiplied by output equal depreciation plus depreciation rate plus population growth multiplied by our capital. I put here little g for savings and capital in order to refer to the golden rule. Then I would like to put s on one side, all other variables on the other side. So I will divide both of them by function of capital, which is our output function. So this will give us our SG equal D plus N kg divided by function of kg. Let's continue. I know that dn, D plus N, is equivalent to what? Our MPK, which is equal to what? The first derivative. So I will write it here as the first derivative multiplied by kg divided by our production function. If we solve for this one, we will get our saving rate at the golden rule is equal to theta. Let's apply it with some numbers from our production function. So we said that our saving rate at the golden rule is MPK, which is the first derivative of our production function, multiplied by our capital divided by our production function. So we know that this is our production function per capita. Our little y, which is a function of capital, equals a k to the power 0.56. And we said we write this little j to refer to the golden rule. So in order to get the first derivative, which is MBK, this is called MBK, which is the f prime kg, I need to get the power of k down. So it will be 0.56. And then from the power, I need to subtract 1. So 0.56 minus 1, it will give us a power of negative 0.44. So our first derivative will be 0.56 multiplied by a multiplied by kg to the power negative 0.44. Then let's substitute in our formula. This formula. What's our first derivative? 0.56 multiplied by a multiplied by kg to the power negative 0.44. Then I need to multiply it by kg. Then I need to divide it by our whole production function, which is a kg to the power 0.56. So here in the power, in the numerator, I have kg twice. One is to the power negative 0.44. The other one is to the power 1. So if I have the same variable, let's get the summation of the power. So negative 0.44 plus 1, it will give you little kg to the power 0.56. So this will give us 0.56 multiplied by a multiplied by kg to the power 0.56 divided by a multiplied by kg to the power 0.56. So I can offset a with a. I can offset kg to the power 0.56 with kg to the power 0.56. So we'll end up with our saving rate at the golden rule is equal to 0.56. We know that this 0.56 is equal to what? Our theta. So we prove that all the time our golden rule saving rate will be our theta, the power of k. Let's move to the next part. Suppose changing attitudes toward marriage and family leads to a decrease in the population growth rate to 0. So now our little n will be 0. Compute the new steady state values and include impact of this change on your figures for 1c. So we would like to calculate our new figures for our little k, little y, little I, little c, and then draw it and see what will happen over time. So we have now, the only difference is little n equal to 0. I have the same depreciation rate of 37.5. I have the same saving rate of 4/5, and I have the same technology, which is 22.5. Then I would start with our formula for our capital at the steady state, which we calculated in the previous videos. So I know that our capital at the steady state, I put star here, which refers to the steady state, saving rate multiplied by technology divided by depreciation rate plus population growth, all of this to the power 1/1 minus theta. Let's substitute. What's our saving rate? 4/9 multiplied by technology 22.5. All of this divided by depreciation rate 37.5% plus our population growth is 0. All of this to the power 1/1 minus theta. Where is our theta? 5/9. Use your calculator. You will get a capital of 1615.96. So this will be our capital at the steady state when we decreased our population growth to 0. So now we just calculated our capital per capita at the steady state. What we need to calculate now is our output per capita. Our output per capita is equal to a little k to the power theta. Let's substitute. What's our a? 22.5. What's our little k? The one we just calculated here, which is 1615.96 to the power theta. What's our theta? 5/9. Use your calculator. You will get our output per capita at the steady state is equal to 1363.46. Then we need to calculate our investment per capita. For investment per capita, our formula is saving rate multiplied by output per capita. Saving rate is 4/9, which was given. Output per capita is the one we just calculated here. So this will give us investment per capita is 605.98. Our last variable will be our consumption per capita. The formula for consumption per capita is output per capita minus investment per capita. Output per capita, which we calculated here, minus investment per capita, which we calculated here. This will give us our consumption per capita of 757.48. Then let's draw it. This is our old production function, maintenance cost and investment function. What will happen to our maintenance cost curve if n decreases? So the whole curve will shift to left. So we're going to shift it here now to the left. Then I would like to look at our new steady state, which is the point of intersection between the new maintenance cost, which is little d plus little n2 multiplied by k, and our investment function. So it will be this point. So from this point, I will go vertically in order to get our capital at the steady state, which we just calculated, which is equivalent to 1616. Then I will look at the point of intersection with the production function, and then I will go horizontally in order to get our output per capita at the steady state, which is equal to 1363.46. And then from our new level of capital per capita at the steady state, I would like to get our investment. So I will look at the point of intersection between this new capital at the steady state and our investment function. We'll go horizontally, and this will give us our investment per capita, which is 605.98. So I know that this area refers to our investment per capita, and then the difference between output per capita and investment per capita will be our consumption per capita, which is equal to 757.48. So as you can see, we didn't shift our production function, we didn't shift our investment function. What happened by moving from the old steady state to the new steady state is capital per capita became higher, output per capita became higher, investment per capita became higher, consumption per capita became higher. Let's move to the next part of the question. Include a plot of the evolution of little y, little I, little c, little k, which is output per capita, investment per capita, consumption per capita, and capital per capita, over time as the economy adjusts from the old steady state to the new steady state. So let's look about the new production function graph. So here if you check here, we didn't change our production function. It didn't shift. We didn't shift our investment function. All what we did is we shifted our maintenance cost to the right, downward. So what will happen? Our capital per capita will increase, our output per capita will increase, our investment per capita will increase, our consumption per capita will increase, but it will increase from what? From the original steady state, which is from T0 till the new steady state. Therefore, it will increase slowly, and that's why it will take this concave shape. Why? Because of the law of diminishing return. When we increase 1 unit of capital, what will be the effect on our total output? At the beginning, it will be higher productivity, and then productivity will start to decrease by increasing an additional unit of capital. Therefore, we'll start from T0 to T1 for all of them, because we didn't shift our production function and we didn't shift our investment function. So let's start here. This is our K1 and this is our K2. So I will start from T0, and then our time will move on and we'll start to have this new transition for capital per capita from the old steady state to the new steady state. The same for our output. We'll discover that I will start from Y1 star to our Y2 star, and then it will increase over time till it reach our new steady state. The same for investment per capita. I will start from investment 1 star to investment 2 star, and it will take its time in order to reach our new steady state. The same for our consumption per capita. Then another point. Provide a brief economic explanation for the consequences of lower population growth rate on current and the future per capita consumption and why. So, anytime we have a lower population growth, it will not affect our production function. Why? Because if you check, it only affects our maintenance cost because we didn't shift our production function. We just moved from one point to another on the same production function. So it will affect only the maintenance cost because N will be lower. Consequently, the whole ratio will be lower. So this would result in having a higher capital per capita because we will have a new intersection point between the new maintenance cost and the existing investment function, and consequently it would result in higher investment per capita and higher consumption per capita. Another point is provide a brief economic explanation for the consequences of lower population growth rate on the long run economic growth. We said that if we decrease N, it affects only the maintenance cost. It doesn't shift the production function. It doesn't shift the investment function. Consequently, we could say that our per capita output growth on the long run in the steady state is 0. It's not affected by population growth. Why? Because mathematically, we could write it as our percentage change in output is equal to percentage change in capital is equal to percentage change in labor, which is equal to little m. So in the steady state, our percentage change in output will be 0. So our last point, does a change in population growth change the golden rule size of the economy? Discuss your answer. So we said if you want to change our little m to be 0, for example, to be lower, will this affect our golden rule? Definitely yes. Why? Because any change in n will change our capital. Let's make a comparison. I made a comparison here before the shock. We have the same M, we have the same depreciation rate, we have the same technology. The only difference is in the question we got a saving rate of 0.44, and then for the golden rule it's supposed to be the theta, which is 5/9, which is 0.56. So what will happen to K? I discovered that when we started to apply the saving rate at the golden rule, K started to be higher, output per capita started to be higher, investment per capita higher, consumption per capita is higher. Then I will make another comparison post the shock. So now I changed N to be 0, but still the same. Depreciation rate is the same. Our technology is the same. Still the only difference is our saving rate is the original one at steady state, which is 0.44, and now I change it to be our theta, which is 0.56. What will happen to K? Capital per capita, it will increase. Output per capita will increase. Investment per capita will increase. Consumption per capita will increase. And we get some of these numbers in the previous calculations, and with the others you can calculate it yourself using exactly the same formulas, and it will be a good chance for you to practice.